process occurs, the mesoscale, the scale of the leaves, and the branching crown of a fractal self-similar tree. And the way that this reactor is scaling from the nano to the macro scale is completely different than from a classical chemical reactor. And there's a lot to be learned in terms of how we do chemical scalability in chemical processes. And this is one of the things we're trying to do, is thinking how do you scale chemical reactors from the lab to the macro scale. And usually you take vessels and you have stirrers, and there's a lot of empiricism, and scalability is a very big issue. And perhaps there is something to be learned about how this actually is done in the tree. There's a parallel between active sites and catalysts, pore networks, and the reactor scale. Now, perhaps we've seen when you came in here that Darwin used to live right next door to here, and so every day I come by there, and so will you. And there's this paragraph there that's related to on the origin of species. And of course, as Darwin showed us, nature has evolved over the eons and has led to some processes being extremely efficient, effective. And so there might be a lot to be learned from how nature has attacked problems that are in effect chemical engineering from the nano to the macro scale to learn us and help us find solutions, sustainable solutions to technological challenges. And that's what this course will be trying to address. So nature-inspired chemical engineering is really looking at fundamental mechanisms behind properties like scalability, efficiency, robustness, and learning from this. And we will take this mechanistic approach, learning about scalability of trees, say, devise new systems like this fractal injector to distribute fluids uniformly over a reactor, to new types of catalysts, force balancing, you see, and how to immobilize enzymes for controlled drug delivery or biocatalysis, or looking at how patterns form in the sand by the action of the wind and the water, instead of being chaotic, to actually structure reactors from being chaotic to very ordered, or to design new self-healing materials. So in this course, you'll look at solving chemical engineering problems, embracing your chemical technological basic skills together with your creativity, and seeing at old problems and very challenging problems, whether it's in water or energy or environment or new types of medical devices, of how do you solve them by learning from nature. And to teach you also a fundamental mechanistic way of doing this and a systematic way. So it's not just looking at nature and then finding some inspiration and there you go for a solution, but there's a very systematic way of doing this. And so we'll have quite a few lectures around how to do this, but more importantly, you will also have projects where you will work in teams of 4 students who will together develop, you will scope a problem you want to solve, and then basically with different milestones through the course, solve and use and apply this methodology and in the end come with an overall report and presentations on this work and get guidance from myself and demonstrators. So in the end, we would like you to think differently. That is what this course tries to do. So it's looking at nature in a perhaps more advanced way to learn fundamentals of natural systems as opportunities for solving problems in engineering, applying fundamentals, and recognizing solutions in the end where this nice approach can be used. So when you work in a job later on, that you can think about this method as a source of innovation, right? As a method to innovate. And so we look at fundamentals systems like multi-scale hierarchical systems, use of fractals, dynamic self-assembly, and then we'll move to applications like from fluidization, reaction engineering, fuel cells, biocatalysis. So we'll really move from integrating pure fundamental new principles, in addition to the things you already know in chemical engineering and chemistry, and integrate this with new vision to come to applications. As part of the course, there will be some critical paper readings from our group and others, which you can then read on and comment. So there's a few of these throughout the term. There's 5 papers, and so then you can put in comments, see other people's comments, and so it teaches you also of how to read research papers, which may be useful also if you have an MSc research project. So overall, the coursework is actually 70% of the overall grade. The project, which I told you about, is working in a team, is 30%. However, there are different project milestones throughout the year, so it doesn't come just very much at the end. So you have guidance throughout. It's just like you have in process design for those that have taken chemical process design. There's only like 2 homework assignments. This is critical paper readings. And so we will help you with that. So throughout the course, the lecturing will alternate with these project milestones and discussions. And more information will always be uploaded on Moodle. So teaching this course on Wednesday, Fridays, Wednesdays 11 a.m. to 1 p.m. in Roberts, which is our engineering building, so next door, and on Friday afternoons with twice a week office hours. And we have two wonderful demonstrators, Nidhi, who has helped me last year also on this course, and Halan, both also PhD students working on nature-inspired chemical engineering. And so you will also have an opportunity to see some demonstrations in the laboratory as well. So it's really a combination of real practice, learning new things, and applying it really to a problem. And I've been really impressed with the projects last year that we've seen. And we hope that those of you who will choose to work on this course will equally produce some make you think differently about challenging problems and see how nature can teach us some lessons and how we could do that. Thank you. Any questions about the course and how it's taught? You know, we all get our 5 minutes, and it's a lot of information. Good, very good. All the best and welcome again.
For those of you who might just arrive, my name is Mikhail, and I'm teaching this course in the second term along with my colleague Dr. Stefan Bulding. So this is the Advanced Material Processes and Nanotechnology course. So the learning outcomes of that would be to make you aware of novel materials and recently developed material processes, understand essential concepts in material science at multiple scales, from the molecular scale up to the phenomenological scale, talking about manufacturing of these materials, and being able to apply fundamental chemical engineering principles like transfer phenomena, chemical kinetics, thermodynamics, etc., in the design and operation of materials processes that involve nanofabrication, templating, and self-assembly. So there are two parts of the course. I personally will be teaching the part that has to do with solid-state processes with applications in the microelectronics industry. So we'll mainly focus on these processes: microlithography, chemical and physical vapor deposition. Whereas on the second part, Dr. Goulding will be teaching things related to soft matter, so soft nanotechnology, soft matter fundamentals, and applications in things like lipids, proteins, colloids, polymers, and emulsion materials, and processes such as self-assembly, chemical processing, and templating. So these are the pictures of the people that will be teaching it. So I'm obviously this person here. And in terms of the lecture times and venues, it's going to be on Tuesdays and Fridays. This is for the next term, right? The second term. The assessment is 20% coursework, and 80% of the final grade will be the exam. This will be a 3-hour written paper, and all questions will be compulsory. The pass mark is 40% for the written, for the overall average that you get from these. Right? This is some reading list. This you can find on Moodle as well when this becomes available. And if you're wondering what's this to do with chemical engineering, I can give you a bit of a preamble. So we'll be talking about a process like this thing here, which is the irradiation and then subsequently the solution of the photoresist film. This has applications when you try to transfer a pattern from a mask into a silicon chip, essentially. And you will see things like thermodynamics, transfer phenomena, and mathematics that go into the development of the model for the dissolution of this photoresist film, which we will discuss in class. There is another example here, which is chemical vapor deposition. So this is a chemical vapor deposition reactor. There are two reactions that happen in this case. So we have to take into account mass transfer and reaction. So this is very much in the heart of chemical engineering, right, to design this reactor. And in terms of so these were examples from the solid matter. And in soft matter, there are some examples on the example of the colloidal self-assembly, in which, again, the description of these phenomena involves concepts from chemical kinetics, thermodynamics, transport, and eventually build a mathematical model of this. And finally, I think this is the final slide. This is a block of polymer co-assembly for inorganic nanoarchitectures. You can get all these interesting patterns evolving in this three-phase diagram. And again, you need all these concepts to be able to describe this and understand the fundamentals in order to manufacture certain phases for these materials that may have applications. All right, so that's it. Do you have any questions? Yes?
Is first chemical engineering degree required to success in the process?
Well, not necessarily, but it would be desirable. So the thing is, some of these concepts, especially the first part, can be quite mathematical, but I go through all the details, so you don't need to know these concepts in advance, but it would help you because it would be the first time that you hear about the field modulus, for example. Right? Anything else? No? Okay, so